Okay, in lesson 10.2, we're going to continue on with our two population means, but in this lesson we will have known our population standard deviation, meaning we have sigma 1 and sigma 2. We don't have to use our sample standard deviation. Of course, this is not really practical because we generally don't have a population standard deviation, or if we did, we would also probably have our population mean and we wouldn't have to go through the whole testing procedure. So it isn't practical, but every once in a while we'll have a sigma from prior year or somehow have a population standard deviation that we are allowed to use. So here are our formulas. You'll notice they look very similar to the formulas we went over in 10.1. So we have our standard deviation of the difference in sample means. It's exactly the same except that I have sigma here and sigma here instead of S. Our confidence interval is going to be the same. We take the difference between the two sample means, plus or minus. We're using a Z now because we have sigma. And I use my sigma here, and note my sigmas kind of look like sixes, but they're actually our sigma, our population standard deviation. And we're going to use our standard deviation that I just gave you. Our hypothesis test, very similar to 10.1. We have our null is that the two population means are equal. So I can say that they're equal, or I can say the difference is 0. Our alternative hypothesis, which I did not write down here, is going to be that we can have less than, we can have greater than, or we can have that they're not equal in case I don't have any information about whether it's less than or not equal to. Just be very careful which population you make 1 and which one you make 2, because it's not always consistent. Somebody could do the test with less than, somebody could do the test with greater than, and still have the same results because they switched their 1 or 2. So the test statistic, remember we're dealing with Z again, and we're dealing with our known population standard deviation. So our formula looks just like the T, but with a sigma instead of an NS. We find the p-value the same way. Remember our p-value, our difference between our sample means is going to be, our difference between our population means is going to be 0. We'll come up with either a Z on the right-hand side that's positive or a Z that's negative, and our p-value is going to be those areas of the tail. So let's go on and do an example. So here I have an example. I have the mean speeds of fastball pitches from 2 different baseball pitchers are to be compared. A sample of 14 baseball pitches is measured from each pitcher. So I know that I have n equals 14 and n equals 14. Okay. The population have normal distributions. And the scouters believe that Rodriguez pitches a faster, speedier ball, or pitches a speedier fastball. So this is going to be my first sample mean, and this will be my second one. Let's let this be 1 and this be 2. And so here I have sigma because it says population standard deviation. So I have my sigma 1, sigma 2. Okay. The first thing they ask here, and this is a web assigned question, so it's similar to what you'll see in the homework. What is the random variable? Well, I'm looking at the difference between my two means. Okay, so that is my random variable here. And I also want to state my alternative, my null and my alternative hypothesis. So my null hypothesis here is that the population means would be the same. There would be no difference. Okay, and the alternative here, and this is where we have to be careful because we used Wesley as 1 and Rodriguez as 2. So they're saying scouters believe that Rodriguez has pitches a faster, a speedier fastball, sorry. And so in that case, we're going to say that the Rodriguez is going to be greater than Wesley. Since Wesley was our 1, it's going to be a less than. Okay, so we have to go through and do our test statistic, and in this particular problem, I'm just going to use my calculator. I have stat, test, and then I'm going to have a 2-sample Z test. Z because I know what my population standard deviation is in this one. On your calculator, this is number 3. And when you're entering in this information, just be careful because it's going to ask for your 2 population standard deviations first, but then it goes and asks for your sample mean of the first one, your sample size of the first one, then your sample mean of the second one, and your sample size. So make sure you put them in the right order. This is going to be a less than problem, and then if I calculate this, I end up getting negative 2.46 with a p-value of 0.007. Okay, so if I actually drew this, I assume my difference is 0, and I get a z that's negative, and I probably didn't put that far enough over. This area should be a little less, but you can see that by the p-value, it's very, very small. Okay, so I'm looking at the probability if my difference between the 2 fastballs is 0, if the actual difference, if I took all of their fastball pitches, not just 14, the probability that I would come up with a sample mean with just the 14 of as far away as I did or further is 0.007. So it's not very likely that the difference in their sample means would be so big if the actual population means wouldn't have a difference at all. So what would I conclude at this one? At alpha equals 0.01, I'm going to reject the null, meaning there's enough evidence for me to state that Rodriguez has a speedier fastball than Wesley, or it's statistically significant is sometimes what the WebAssign uses. So you can see that in this problem it's exactly the same as what I did for my t-test. I just have to use my number 3, my z-test, and I'm going to come up with the same type of conclusion, either reject or don't reject, based on my p-value.